about just introduce branching processes and maybe Poisson processes. So this is pretty much a pure probability talk, which is nice, I guess. So it's not that much networks. So let's start with branching processes. So formally they're called Galton-Watson processes. But I'm going to say branching. That's what I call it. So the concept is pretty simple. We start with one individual. So this is like population dynamics modeling how many individuals are in a population. So we start with just one, and then that one gives birth to a random number of children. 4 maybe. And then each one of them independently gives birth to some other random number of children. It's possible that they don't give birth to any children. And so let's see, how this we can call, we're going to use Z for the number of individuals in a generation. So Z0 is 1, Z1 is 4, Z2 is 6. And all that's really driving this is some underlying variable or some distribution that tells you how many individuals does every individual give birth to. So I'm just going to say there exists a random variable, I'll call it X throughout, that takes integer values, non-negative, such that every individual gives birth to xi children. We index it somehow. So this is individual I gives birth to xi children. Where all these x1, x2 are independent. And distributed like X. So basically, independent copies of the same random variable. So the distribution of X is the offspring distribution. Basic description of the problem. Well, we don't really have a problem yet. We're not asking it at this point. So who's here? Have you seen this before, everyone? Or okay, some people haven't. So a typical question is, well, the first kind of question is what's the distribution of the ZIs, right? Yeah, how many individuals are going to be in the nth generation? And answer that, but first let me talk about probability generating functions. So for a random variable, we define a function. So for a random variable x, it's PGF. Probability generating function is, say, fx of s, which is the sum of, again, again, we're assuming x takes non-negative integer values, because again, this definition is more general than that. Just to make it simpler. It's given by this, which you might recognize if you've seen generating functions in discrete math. The easiest way to write it is just the expectation of s raised to x. Okay, and this is also the most useful form of this. This is basically, I think, the Laplace transform or some sort of transform of the random variable. Basically, in the probability that we're doing, discrete probability, everything's nice, everything behaves nicely, and so on. You could. There are other things called like the moment generating function, where you take e to the tx. I think that one's actually exactly the Laplace transform. You can do the characteristic function, which is a Fourier transform of this variable. Basically, in the sort of discrete probability we're working with, they're all the same thing. So we're just doing this because it's simplest. But you might as well use, you could have used these two, but it's just plugging in e to the t instead of s. So, and the probability generating function contains information about the distribution of x. So you can go between a distribution function and the probability generating function in a way that's useful. So let's see. Probability generating functions are very useful when it comes to branching processes. So let's see, Fn of s is BGF of Zn. So that's the variable we're interested in. We want to know the distribution of this Zn. So what we're actually going to do is find out the PGF of it, and then sort of read off from that what the distribution is, if possible. There are techniques of going between them. Let's not get into it. It's pretty elementary. You can just take derivatives and plug in the right thing. So we're focusing on this Zn. So we know that this is going to be the sum of a bunch of xi's where I goes from 1 to Zn minus 1. All I'm saying with this identity is that the number of individuals in the nth generation is all the children of the n minus 1th generation. So every individual in the previous generation contributes one random variable. And indexing is just some indexing. So that, yeah. The point here is that it's the sum of this many copies of that, of the x variable. Okay, so let me say again, they're independent. So we want to find this Fn of s. So it's equal to the expected value of s raised to Zn, which is the expected value of s raised to this sum. So here we want to use the fact that these xi's are independent, so then we can break up the expectation into separate factors. We can't really do that yet because the number of terms is random, but we can just condition on that. So let's see, we're conditioning on the value of Zn minus 1, so the number of individuals in the previous generation is, let's say that's k from Poisson k at least 0 times what we did here is the law of total probability, I think it's called. This is how you condition on a random variable. You sum over all the values of it, and then you can condition on z n minus 1 having that value. So you sort of weight it against the probability. Like if you've seen this before, it's pretty elementary. If you haven't seen it before, I don't know, maybe it looks weird. Anyway. So this expression here, this conditional expectation, if we condition on z n minus 1 being equal to k, we can just write it as just replace that z n minus 1 by k. And now this is a product of a fixed number of independent random variables. We can break it up. And since they're all independent, they're all just going to give the same expected value, so expected value of x1. And now, maybe I should have said what the goal was of this, but now maybe you can see what identity we can get from here. So this is, if we think of this expected value here as just a variable, then this is the definition of the probability generating function for z n minus 1. So this is that. So we've showed that what we started with was fn of s. We have this identity. And inductively we can show that, well, we just showed pretty much. The nth PGF is just this underlying offspring distributions PGF taken n times. So I'm going to say, yeah, this for composition. Okay, so that gives us a pretty nice way of finding the probability generating function. Most of the time, it's not going to be a nice expression, though. But this is a very useful identity. It can give us some nice things. I don't know if the food's ready. This would be a pretty good time for a break. We can do an example. So, the nicest example I can think of is if x is geometric, which just means that the distribution is the probability that x is k is p times 1 minus p raised to k minus 1 for k at least 1. This is a very common random variable. P is just a fixed constant between 0 and 1. Then this probability generating function is, well, when you plug it in the definition, it's basically going to be a geometric sum, and you'll get ps over 1 minus s times 1 minus p, which I'll write as p over 1 over s minus 1 minus p. Now this is very nice to sort of compose with itself, because if we do this n times, what we're getting is p to the n divided by 1 over s minus 1 minus p to the n. So if you sort of read out from this that Zn is geometric with parameter p to the n. And in particular, we can say that e to the expected value of x is 1 over p, and the expected value of Zn is 1 over p to the n. And this last line here is going to be sort of an example of a more general rule that's easy to show, actually, that the expected number of individuals in the nth generation is always the expected value of x raised to n. So regardless of what x is, this is going to be true. There's a lot of calculations here. So this is also pretty easy to show. Debating whether or not to do it. Well, let's take a break.
Sorry guys. Everybody after same.
Okay, so before I finish this sort of introduction to branching processes, I should mention the sort of famous theorem, or like the sort of central fact that you always use when you talk about branching processes. So the probability that there exists an n where there's basically the probability of extinction. So let me frame it like this. Probability that some generation is empty means that every generation after it is empty. This is 1 if the expected number of offspring is 1 per individual, and it's eta if it's bigger than that. We all know what eta is. Where eta is the smallest solution, smallest negative, to the fixed point equation for this fx. Okay, so that's a pretty cool fact that I'm not really going to use, but that's sort of what you should know about branching processes.
What if it equals 1?
Huh?
What if the expectation equals 1?
then it almost, so the only way it can survive if the expectation is 1 is if it's always exactly 1. So, because if,
okay, yeah,
yeah, pretty much. Okay. If there's any variance at all, then it's going to go to 0. Yeah, this, like branching process in random graphs, come up a lot, which is what I do with random graphs. Basically, if you have a random graph and you want to start at a vertex and search for all the neighbors within a certain neighborhood, within a certain distance, then the first few steps always basically looks like a branching process. So that's why I'm interested in them. They come up all the time. When you're sort of looking for, when you're doing a breadth first search, which is like a very common graph algorithm. That kind of stuff. Poisson processes are not as common in discrete probability, I'd say, even though they're kind of discrete in a way, I guess. So I don't see them that often, but they're very like central stochastic processes. If you're doing probability, you know all about it probably. So this is, I guess the easiest way to do it is a process, a sequence of events at time, I don't know, events, most of the time I call them arrivals. That's how I think of it. So it's x1, x2, so I'm just going to draw a picture. So we start at time 0. And then we wait. So what I think of this, the easiest example I think is like you're sitting on the sidewalk noting when cars go by. Or like you're next to a highway or something. So like cars come totally independently of each other. You can never, cars and then another example is like radioactive decay. So when you look at an atom, you never know when the next sort of decay is going to happen. The next time it's going to shoot up a neutron or whatever they do. But I know that that sort of follows the Poisson process. It's a totally unpredictable process, in a sense. So I'll say, at any given time, so I don't just want to give you the definitions, I want to give you like why this is special. Or like, I want to give you the properties first and then tell you which distribution has to be here. Not that I know why that is the case, but at any given time, the random time, oh yeah, I should mark these right. So we have like x1, x2, x3, x4. We're just keeping track of when something happens. Oh, it comes up a lot in like queuing systems. If you're like at a bank and people are coming in at random times, you want to find out when's the next person going to come in. Most of the time that's totally unpredictable, which is what we're going to do. I'm going to stop trying to motivate this time. So the random time until the next arrival is independent of the history. Okay, so this is not the Markov property, by the way. It sort of sounds like it, but if you think that's what it is, it's not. But so it means that even if you know we're at a bank, see a parking flow, for example, we just had a customer walk out the door. That doesn't give us any information about when the next customer is going to come in. It's going to be sooner or later. And in the same way, if we sit there for an hour and no one comes in, that still doesn't tell us anything about when the next customer is going to come in. So for some sort of distributions, some processes, they would be like, okay, now we've been here for an hour, we know for sure that someone's going to come. But for these processes, it's like waiting for this food. You never no, but so basically the sort of cool thing about this is that the distribution of inter-arrival time, so the time between arrivals, has to be the exponential distribution for this to hold. So this is only possible if xi minus xi minus 1 is exponentially distributed. Exponentiality. So I'll say that xi is the sum of t1 plus t2 plus ti. So in this picture, t1 is the time between 0 and x1, and t2 is the time between x1 and x2, and so on. Where ti is exponential distributed, I'll say the probability that ti is greater than t, so this is a continuous time distribution, e to the negative alpha t for some alpha, constant alpha. Okay. So this is not like completely true, or like this sort of suggests that I'm saying, well, I did say constant, yeah. So it's not true that it has to be constant. It can be varying, like inhomogeneous Poisson process where the rate of arrival, which is this constant alpha, but that keeps changing. If we want to do the example of, bank, certain times of day, the rate of arrival could be higher, so that we expect sort of shorter time in between. But the processes I'm going to talk about, we're always having some constant alpha that doesn't change in the process. So the sort of variable that we're interested in is the number of arrivals in interval of time. So define n of t to be the maximal k such that t1 plus tk is at most t. So this is the number of arrivals up until time t. Then n of t is Poisson distributed. So I just write Poisson rate alpha. These names of distributions you don't need to know. I'm always going to tell you what the distribution is. The probability that this is k is going to be, it's alpha times t. E to the negative alpha t times like this. So kind of exponential, like the geometric one, not really. This one is not nice to work with in regards to like branching processes, where we sort of iterate the probability generating function. It's going to look awful. That's exactly what we're going to do. Well, almost the same. Okay, that's nice. But the really nice thing is that if we condition on which which is probability talk for just saying if we suppose that this is true, then x1 through xk, the arrival times, if we sort of ignore the order they have, this set is where they are independently uniformly distributed. In the interval 0 t, which is really nice. So instead of like running this process with exponential random times and like doing it sequentially and finding out what's in here, if we can sort of do it the other way around. We draw this random variable, we ask, okay, what's this Poisson variable? How large is it? We get k, and then we just sprinkle those k arrivals in this interval uniformly and independently of each other. That's extremely useful when it comes to Poisson processes. And we're going to see why. So that's kind of all we need to know. They're very, very interesting, very like central to stochastic processes. There's lots more to say about it, I guess. And there's so many variations and stuff on it. But this is all we need to know. So I think that's all we need to know. So now comes the fun part, where we go from like these very basic things to something very complex. So I think they have different names. I'm calling them Crump-Mode-Jagers process. I think maybe they can classify as Bellman-Harris processes. I don't know. So they are a combination of Poisson processes and branching processes. So let P naught be a Poisson process. Of rate alpha. Yeah, this alpha is called a rate. It basically tells you at any given time in a Poisson process, if we look epsilon ahead, so and we look epsilon time units into the future, the probability that we get an arrival in that time is alpha times epsilon plus lower order terms. So that's basically the derivative, I guess. You can probably do something with the derivative where alpha pops out. Sure. So we start with some process P naught. This is it. This is just best explained by a picture. So we have an arrival here, let's say, at x1. Every arrival gives birth to an identical Poisson process. Identically distributed but independent. And every arrival in a subsequent process gives birth to an identically distributed process. Something like this. Now, and we have a time scale here, so let's see, this is t equals 0. This here is t equals 1. I told you that, no, I didn't. So every process is on an interval 0 to 1. It's on a finite interval. So every process has length 1. Everyone has rate alpha. They're all independent. Now the question we're asking is, at any given time, can we figure out the distribution with the probability that the number of processes alive at that time is k? So let me say that. So let d of t be the number of processes alive at time t. So yeah, this time here is equal to 3. So we draw a line, a horizontal line, and see how many processes it intersects. We want to know the distribution. So what is the distribution? What is the probability that DFT equals K? Now this is not the same as asking about the number of individuals in a generation for branching process. Let's see if I can think of a counterexample here. Yeah, these two processes are both second generation, but they're alive at different times. So like, yeah, I think it's pretty easy to see that, you know, basically the set of individuals in a generation do not have the same lifespan. They may not even overlap at all when they live. So this is a different question, but it has a similar answer. It has a similar method of solving it. It's going to be generating functions again, probability generating functions. So define the PGF of d of t is going to be a function of two variables. So this again is s raised to d of t is random. And we want to do something similar to what we did before. So note that if the initial process P naught has arrivals x1 through xk, then we can partition every subsequent process into which one of these it sort of came from. So we get a partition into k families, basically k processes that are essentially identical to the whole process. So if that's true, then I'm going to say that d of t is equal to summing them all. So I'm going to give these an index just to distinguish them as different variables, being completely independent of each other. Right, so if we look here, we had two arrivals in the first process. So this one came from number 1, and then this x3 what happened in a process that came from number 1. So it's basically the label here is hereditary. So we get every process gets a label between 1 and k, and it always inherits it from the one above. So I think this should be clear. So we can treat these as independent processes. And then, of course, the xi are not deterministic, they're random, and from the observation before, they're going to be independent uniform variables. So we can write this probability generating function. It's going to be equal to CS. We have there's going to be a lot of randomness in here, but basically I'm not going to be totally formal here, but this is a sum of n processes where everyone starts at t minus xi, where the xi's are uniform 0, 1. So we assume t is bigger than 1. So we assume that the first process is dead. And it's similar in the other case too. So what I'm going to do here is I'm going to first condition on the number of arrivals in the first process. is Poisson distributed with rate alpha. That's the total number of arrivals in one process. So it's that, and then this expectation becomes S raised to D1 and the argument is very similar to what we did before. So again, we know the distribution of this is exactly e to the negative alpha k divided by k factorial. And then this thing, these are all independent. It's k independent processes. And I'm going to say that this is, I never really said what the xi's are. Like this. So here are all the xi's and the x. These are not the same xi's and x that I used before, by the way. So here x and x1 and so on are uniform. Zero, 1, and independent. Right, so this sum here is a sum of k independent, identically distributed random variables. So we just take one of them and we get this. Now, as we sum this, it looks a lot like the series for the exponential function. So I'm going to keep going here. This is e, so e raised to alpha times the expected value of this minus alpha. Right. So we've shown now, so this expectation of s raised to g of t, that was f of st, so f of st is equal to the right-hand side, which is this expected value over x, which is a random variable, is just the integral from 0 to 1 of the expected value. We assume that it's equal to x. Yeah, like this. So this is, again, a conditional expectation. We're conditioning on the value of capital X, which is uniform. We don't see the distribution function here because it's just constant, equal to 1. But basically, this is alpha times the integral of f as t minus x. So we have an equation for this generating function f of st, which is not a simple equation, but if you stare at it for a couple months, you can solve it. So I solved this. So this is only for t bigger than 1. So I'll say if t is less than 1, and this x, we get an s in front here times the expectation of alpha is this. Something similar. I can tell you what the solution is when t is less than 1. Let's see. So when t is less than 1, it's not that hard, I think. Just one maybe. To see that this is equal to it's geometric. I brought up the geometric one before, so it's e to the negative alpha t divided by 1 minus s times 1 minus e to the negative alpha t. So yeah, what we will read off from here, GOT is geometric. So the probability that it's equal to k is like that for k greater than or equal to 1. And it's not surprising that it's a positive random variable because the initial process is still alive, which is less than 1. So it has to be some distribution that's always non-zero. Now, this thing here, we can rewrite it as a differential equation. So this equation, like star, if you take logarithms, then differentiate with respect to t, you get df dt equals alpha times f st squared minus alpha f st f of s t minus 1. So it depends on basically the way how to solve these. So we have a solution on the interval t between 0 and 1. That gives us enough sort of initial, an initial condition for the solution on the intervals 1 to 2. And that solution gives us 2 to 3 and so on. So you have to solve it inductively over every interval of length 1. And you get something which is terrible, but in general, f of st is 1 minus q of t plus p of t, what is it? There's an s here. I'm not just doing this to show you how complicated everything is. I'm just, this looks a lot like the geometric one. Just a slight difference in the beginning. So if we look at this, this is 1 minus q of t plus q of t times the EGF for geometric. So and you can sort of read off from here what the probabilities are. This is a Taylor expansion for this probability generating function, and just from looking at the k coefficient, we get the probability that this d of t equals k. I'm just going to say qp times 1 minus p a minus 1 if k is greater than or equal to 4. So that's sort of how we can use generating functions to solve these problems. Is there anything else I want to say? And the functions q and p, again, messy, but basically exponentially decaying. And it's not surprising that the sort of k equals 0 event has a different probability that doesn't follow the same formula, because in this process, if it ever dies completely, then that's it. But as long as the process is like that one individual is still alive, that it can still fluctuate, sort of, it makes sense to me that this is an absorbing state equals 0, and it sort of should set it aside from everything else. Formulate. I guess I don't have time to explain why I've been looking at this, but it has to do with random graphs. So. Yeah, I think that's. Maybe.
Alright, let's try Antonio again.